All right, hello everybody. Welcome back to the brain chapter 14, part 2. In the first part, we have looked at some general properties of this central nervous system organ. We looked at individual aspects of the brain stem, of the cerebellum, and the diencephalon. The fourth and the largest part of the brain is the cerebrum. This illustration here shows you a detail of the surface of the cerebrum, and the surface has a unusually emphasized feature: large peaks with deep valleys in between them. These peaks or ridges are called gyrus, in plural gyri, and the valleys between them that can go very deep, as you can see in this cross section. That is the sulcus or sulci in plural. The gray matter of the cerebrum is tremendously increased by this arrangement of the surface, because a very large surface area can be jam-packed into these roller coaster-like waves of gray matter. This is the cortex part of the brain, and a lot of functions that we associate with conscious sensory or motor activities play themselves out here. Later on, we will name two very specific gyri with associated functions, and we will talk a good deal about the function of this cortex portion of the cerebrum. You do see that there is a good deal of white matter. We mentioned that too later on. I also have to say that not captured on this image, deep inside the cerebrum, there are clumps of gray matter, ganglia, and some other structures. We will talk about that too later on. So cerebrum, the operational aspect of the cerebrum that makes this most attention-getting is that all conscious activities are carried out by this part of our brain. If you inactivate, destroy cerebrum, you destroy the ability of that person to be conscious, to feel, hear, taste, smell anything, or to consciously control skeletal muscles. The rest of the brain, the diencephalon, brainstem, cerebellum, can function on their own. Our cardiovascular system, respiratory system may still be actively managed by the rest of the brain. Total inactivation, functional inactivation of the cerebrum is typical for long-term disorders that come with a coma. Coma is the lack of consciousness, and that means the cerebrum is, for one reason or another, is knocked out of commission. We also lose the activity of the cerebrum when we are asleep. We are conscious only when we are awake, and switching between wakefulness, consciousness, and sleep is one part of the hypothalamus and reticular activating system. That is the exquisite importance of those structures turning on or off the cerebrum, whether we are awake or when we are asleep. Also, when we faint, such as a consequence of hypoxia, choking, or losing source of oxygen, or when we are hypoglycemic, again, this part of the brain is responsible for shutting down conscious activities, and for us, that constitutes fainting, loss of consciousness. When people faint, they limp, they can no longer control skeletal muscles, so that's a perfect association, cerebrum with control of skeletal muscles Once you deactivate the cerebrum, whether it's sleep or fainting or coma, the individuals are no longer controlling skeletal muscle. They cannot maintain balance, and they fall down. Gross anatomically speaking, the cerebrum has two hemispheres, left and right, and in each hemispheres there are lobes. On a cross section such as one that you see here, you see this arching light colored material. This is the corpus callosum. There will be better images. That is the connection between the left and right hemispheres. So corpus callosum is still part of the cerebrum as a connecting bridge between the hemispheres. The lobes themselves are roughly named after the cranial bones that form the arching protection. So here's frontal lobe, we have parietal lobe, we have occipital lobe. Laterally, we have the temporal lobe, and on this X-ray-like feature folded under the temporal lobe is the insula, the fifth lobe of our cerebrum. There are gross anatomical structures that separate lobes from each other and the hemispheres from each other. Those are given the name sulcus. So let's see the first one. And I'm sorry, this is going to be the fissure because it separates the two hemispheres. So this is the longitudinal fissure, separates left and right hemispheres. A sulcus that we'll come back to later on is the central sulcus in yellow. We will be named specific gyruses. So here's the pre-central gyrus anterior to the central sulcus, and there's the post-central gyrus in both hemispheres. We have extremely important functions related to these two gyruses, related to our conscious perception and control of skeletal muscles. We also have separating these two lobes, the parieto-occipital sulcus. We also have the lateral sulcus separating the temporal lobe from the parietal and frontal. So this is the bird's eye view of our cerebrum with the lobes, one fissure, and several of these sulci. This is a much better view of the corpus callosum. You can see this arching structure. This is nothing else but billions of axons crossing from the left to the right and from the right to the left hemispheres. So this is pure white matter. Besides this very obviously white matter, bundles of myelinated axons are going through the corpus callosum. We do have a huge amount of white matter deeper inside our cerebrum. You can see the cortex, this little almost like milk chocolate brown layer here. But between the corpus callosum and the cortex, there's this huge area that is dominated by white matter. So just to review, white matter is nothing else but bundles of myelinated insulated axons. So axons carry information from one point to another, and if we are carrying information between two gyruses in the same hemisphere, those are called the association fibers. Here's an example of that. From one gyrus right here, fibers are going into the other gyrus. Those would be association fibers. Commissural fibers carry information from one hemisphere to the other. Corpus callosum is a perfect example of a commissural fiber. Projection fibers form the descending and ascending tracts. So information sent out of the brain will be leaving through descending tracts. Information coming into the brain, sensory information coming through the ascending tracts. Outside of the cortex, here are the examples of a few clumps or sometimes really weirdly shaped clumps of neurons. You can see the wonderful cortex with all the gyruses and sulci. In this very lightly shaded area, this is where our lateral ventricle is. So this is a fluid-filled chamber. And just a little bit under and lateral to that, here is this very weirdly shaped group of neurons. So this is gray matter. They are called nuclei or ganglia. And so the basal ganglia, the sum of all these individual nuclei and processing centers have a very important role in coordinating skeletal muscle movement. It is in chapter 16 when we take a look at how precise movements of our limbs, for example, are controlled by one portion of our nervous system, and large automatic movements such as maintaining balance, carrying out walking, running, those movements are controlled by a separate set of structures in our nervous system. So when it comes to automated movements, movements that we no longer pay very close attention to, we take those for granted. Those are coordinated in part here by the basal ganglia. We have substantia nigra, the red nucleus. We mentioned these as coordinating skeletal muscle movements. So basal ganglia are connected to this connection to the cortex, the thalamus and hypothalamus. The functional aspect of all this will be coming our way in chapter 16 in AMP2. We have even weirder looking groups of neurons. The sum of these is called the limbic system. So this is where emotional responses are decided or partially integrated. We have seen the hypothalamus playing a role in this, but the limbic system, especially the amygdala part right here. Amygdala means almond, so this is an almond shape and roughly an almond sized clump of neurons. This is an important coordinating center for swings of emotions, pleasure, pain, and also happiness, sadness. There is another very unusually shaped portion of our limbic system. This is called the hippocampus. The hippocampus is where our short-term memory is housed. In Alzheimer's disease and many other dementia patients, this is the portion of the brain that starts degenerating. Loss of short-term memory is very typical in early mid-stage dementia patients, and this is the part of the brain where neurons just start dying and they can no longer fulfill that storage of short-term memory. On the cortex portion of the cerebrum, there are a number of areas that are closely linked to our most prized conscious activities. So let's take a look at the sensory areas. Look at that list here. Visual area, this is where everything we see with our eyes become conscious experience. Auditory area is the part of the brain where everything that we hear through our hearing apparatus becomes conscious experience. Gustatory area is the area where everything we taste becomes conscious experience. So let's say you're eating that very spicy Chinese food and you detect that very spicy feeling right here in the temporal lobe. If this portion of the temporal lobe is destroyed or missing congenitally, then no matter what food you eat, while your taste receptors are working fine, you would not feel the taste of that food item. So for any nerve impulses coming from our sensory organs to become conscious experience, we need this processing center. Same here for the visual area. You may have the best visual apparatus, best eyes, but if something is damaged or destroyed in the primary visual area, what you are seeing with your eyes would never become conscious experience. In plain English, you would be living in dark. You would not see absolutely anything. So same is true for the auditory area. Right here in the temporal lobe, we have a group of neurons that process nerve impulses from our hearing apparatus. If this group of neurons are destroyed or damaged, then anything that is coming through your hearing apparatus would not be a conscious experience, so you would not hear anything. You would be completely 100% deaf. This is the importance of these groups of neurons connected to sensory organs. Let's say a few words about these. You have seen the origin of nerve impulses that are coming to the somatosensory area. Think about those Meissner corpuscles, Pacini corpuscles in the integumentary system. Somatosensory just means that the sensory receptors are distributed throughout the entire body. And skin is the largest organ, so any receptors that are located in our skin, whether they are pain receptors, temperature receptors, touch, vibration, itch, tickle, everything that we detect with our skin creates a nerve impulse from those sensory receptors such as Meissner corpuscles, and they are streaming to the first named gyrus here, the post-central gyrus. So the post-central gyrus, do I have an animation here? Yes. So the post-central gyrus is this blue one. All nerve impulses from our skin and some other sensory receptors scattered in our body streaming here. These neurons make it possible that you feel that you touch something, that you stick your hand in ice cold water, that temperature sensation becomes conscious experience because of these neurons here in the post-central gyrus. We can put it in a different way. If we would not have any of these sensory areas of our cerebral cortex, we would be living in a dark, quiet place. We would be floating in mid-air because we wouldn't even be able to detect gravity on our feet or on the rest of the body. So that would be total sensory deprivation to miss all these groups of neurons. And think about the highly visual and highly sensory dependent lives today with the smartphones, with Alexa and the rest of the gadgets that we have around us. Everything that you learned throughout your entire life, your life experience, some people would say the things that made us who we are all possible because of these neurons. Without them, we would have no sensory experience. We would have not experienced anything from our environment. Pretty nifty group of neurons here. So their job is to create a conscious experience of the incoming nerve impulses from these sensory organs. We do have a set of neurons. Let me use my animation again. A group of organs that carry out another aspect of our consciously conducted lives is control of skeletal muscle. Every time we get out of bed in the morning, we never think about it. Let's just use the precentral gyrus to get out of that bed, get out of that horizontal position. Yet we need to give commands to those muscles. All those commands that make you sit up in the bed, stabilize your torso, lift up your head, put your feet on the ground, all coming from this portion of our brain. So, and everything from walking to running, riding the bicycle, every time you use a skeletal muscle, including moving your eyeball, moving your diaphragm for inhalation, all those skeletal muscle movements are directed from here. The first nerve impulse is fired in the precentral gyrus. Very important if you think about that. Without this precentral gyrus, we would be totally immobilized and we would need for a ventilator to carry out our respiratory activity. We also have a special area, the motor speech area right here. This is controlling or coordinating movement of tongue, airways, upper airways, oral cavity, orbicularis oris muscle to produce speech, which is pretty important for human communication. So we have managed to detect a visual nerve impulse and create a conscious experience out of it. We also have to interpret that. Anything that you look at has a color to it, has a shape to it. It might be moving in a particular direction. You may immediately decide, I like this, I don't like this. All those reactions to what you see and all those interpretations are coming from the association areas of the cortex. So very large areas are manipulating and processing visual information, but we do have the somatosensory association area. This is telling you whether the temperature you're feeling is cold or warm enough. Is it meeting your expectation? The auditory association area can interpret whether what you're hearing is a natural sound of rustling of the leaves in the wind, or is this a jackhammer? We also have the Wernicke's area that is processing sound of human speech, and this area is responsible for translating those sound waves into actual words with actual meaning. Just a few words about differences between the two hemispheres, left and right. When it comes to conscious and cognitive capabilities, the two hemispheres are not equal in their processing specialization and processing properties. You see a few differences here. I just have this here mostly for entertainment purposes, that damage to the left or right hemispheres do not come with the identical consequences. We may stand to lose more function if stroke or physical trauma inactivates the left hemisphere as opposed to the right hemisphere. Here is a point when we go back to the action of individual neurons in our brains. So here you see this magic word, action potentials. During wakefulness and even during sleep, some part of our brain are producing billions of action potentials every minute. We have 100 billion neurons in our brain. A single neuron can produce an action potential in about 2 milliseconds. So every second, each neuron can produce about 1,000 or so nerve impulses, action potentials. With each action potential, sodium and potassium ions move with the depolarization and repolarization phases, and all that movement of positively charged ions create an electromagnetic field. That electromagnetic field can be detected by a human contraption called the electroencephalographic device, and the changes in the electrical field can be plotted out on paper or on a screen, and that is the EEG, or electroencephalogram. Nowadays, functional MRI has displaced many previous uses of EEG. Different EEG patterns can be assigned to as signs of epileptic actions, seizures, infectious diseases, cancers. Again, other imaging devices have been replacing steadily EEG, where functional MRI has not made an inroads just yet. That is the decision about brain death. Usually electroencephalogram EEG of the brain stem is taken, at least in some states, as evidence that this person is brain dead. The person may not be physically dead because machines may maintain respiratory and cardiovascular activity, but hospitals, nursing homes may use, in some states, EEG as evidence where the family needs to make a decision whether to keep this person on this life support or discontinue the life support. We have a number of cranial nerves that you have already met. Think about those openings on the skull that we reviewed most pointedly maybe in the bone lab. Think about optic foramen, the olfactory foramina. Those are the bony surroundings of cranial nerves. So cranial nerves are thinner or thicker rope-like structures that exit the brain. So cranial nerves are now part of the peripheral nervous system, or PNS. And what's coming in the next few minutes is an individual look at cranial nerves and mention some function. So one word before we do that about the content of these cranial nerves. So imagine millions of axons bundled together in a rope-like structure, the cranial nerve. In the spinal nerves, half of those axons were sensory and half of those axons were motor. In the case of cranial nerves, there could be extreme domination either to the sensory or to the motor side. So we will also mention where the cranial nerves are mixed and mention the sensory and motor functions separately. Again, sensory function relates to making a highway for nerve impulses that are moving into the brain, detecting the change in the environment. Motor nerve impulses are carrying nerve impulses to skeletal muscles or glands to direct their activities. So cranial nerve 1, olfactory nerve, is actually a bundle of, several bundles of axons going through olfactory foramina. If you remember the cribriform plate, it has dozens of openings, olfactory foramina, and so cranial nerve 1 is not a single rope-like structure, but a group of bundles of axons passing through the olfactory foramina. So the function of olfactory nerve is to carry smell-related nerve impulses to the brain. This is purely sensory. Cranial nerve 2, again, sensory, carries vision-related nerve impulses to the brain. Here we have cranial nerves 3, 4, and 6 grouped together. These are motor cranial nerves. They carry nerve impulses to skeletal and smooth muscles of the eyeball. Our eyeballs are moved into very precise directions by these skeletal muscles that look like these strap looking structures. They are under the direction of these three cranial nerves. In AMP2, we'll be naming individual muscles that innervated by individual cranial nerves. Here, it's just good to know that cranial nerves 3, 4, and 6 are carrying nerve impulses to muscles that move the eyeball. Cranial nerve 5 is a mixed cranial nerve motor portion. Muscles of mastication. In a muscle lab, you must remember temporalis, masseter, and there are some others that we did not name, but these are two names you recognize. So cranial nerve 5 is carrying nerve impulses to those skeletal muscles, and the sensory portion is collecting touch, pain, temperature, sensory information from the skin of the face. The sensory portion also penetrates into the oral cavity. So if you have any dental procedures or you have a toothache, that pain sensation is coming to your brain courtesy of a branch of cranial nerve 5. Cranial nerve 7. It has a motor portion, so this is also mixed. Muscles of facial expression receive their nerve impulses through cranial nerve 7, and also salivary glands and some of our tear glands, the lacrimal glands. The sensory portion is collecting taste-related nerve impulse from the anterior 2/3 of the tongue. Cranial nerve 8. You have seen the opening, the internal auditory meatus that leads this cranial nerve out of the temporal bone. This is related to the special sense of hearing, also equilibrium, and that's good enough to know about cranial nerve 8. Auditory or vestibulocochlear nerve is the other name for it. And maybe this is a good time to mention that cranial nerves has a Roman numeral. You can see it on these images, and a name. So on your chapter quiz or on your comprehensive final, please be prepared to identify cranial nerves by the Roman numeral and also by their regular name. So please be ready for understanding and using both terminologies. Cranial nerve 9. This is the glossopharyngeal nerve. Its motor portion carries nerve impulse to the muscles of the throat. This is a very important muscle for swallowing. Another time when cranial nerve 9 gets activated and sends and activates swallowing is when we have the gag reflex. If you ever experienced a swab or a tongue depressor touching the back of your mouth, what's called the oropharynx, that creates a gag reflex, the swallowing reflex, and your cranial nerve 9 was activated in that process. Cranial nerve 9 also carries motor nerve impulses to the parotid gland. This is one of those salivary glands. And the sensory portion of cranial nerve 9 is collecting taste-related nerve impulses from the posterior 1/3 of the tongue. Cranial nerve 10. This is the weirdest cranial nerve. This is also called the vagus nerve. Cranial nerve 10 no longer remains in the neighborhood of the head. This is the first cranial nerve. We'll have one more that leaves the head area. Take a look at cranial nerve 10. It enters the thoracic cavity. It carries nerve impulses to the heart, to some blood vessels, carries nerve impulses to bronchioles in our respiratory system, and then a branch crosses into the abdominal cavity, very, very far from the brain. And in the abdominal cavity, many organs of our digestive system, liver, pancreas, stomach, portions of the small intestine, portions of the large intestine are all innervated by this cranial nerve 10. So this is a major nerve that will come up in chapter 15. In chapter 15, you will hear about the parasympathetic division of our autonomic nervous system. Cranial nerve 10 is a major cranial nerve that delivers nerve impulses that directs and coordinates a large number of organs, as you can see here. Major stimulator of our digestive system. It slows the heart rate. Many activities. The individual details will come out in AMP2 when we talk about the respiratory, cardiovascular, or the digestive system. This is another cranial nerve that leaves the general head and neck area. Cranial nerve 11, the accessory nerve, innervates some muscles of the throat area and the soft palate, but a branch innervates the sternocleidomastoid muscle. You are intimately familiar with this through the muscle lab, and also the trapezius. So these two large skeletal muscles plus the muscles of the throat and the soft palate makes this a motor nerve. This is cranial nerve 11, or the accessory nerve. And our last cranial nerve here, cranial nerve 12. This is also called hypoglossal nerve. This is a cranial nerve that controls the movement of the tongue. And while it doesn't seem like the tongue needs a whole lot of control, what could the tongue possibly do? As it turns out, and if you look back at chapter 11, this is one of the hidden reasons why I put a little slide there about the muscles that make up the tongue. Tongue is not just a single mass of skeletal muscles. There are many individually controlled muscles that make up the tongue and moves the tongue. So this fact of many muscles acting in a tongue creates the opportunity for very fine-tuned control, and that control we need to start the swallowing movement and mostly during speech. Without a sophisticated control movement of the tongue, human speech would not be possible. One sign, if you hear public announcements about signs of stroke, one sign of a stroke is slurred speech. Stroke affecting the part of the brain that sends nerve impulses through cranial nerve 12. Those parts of the brain suffer the damage, and now nerve impulses are no longer coming down to the appropriate skeletal muscles, and tongue movement is impaired, and the result is speech is slurred. So this is the end to chapter 14, and I'm going to close here, and hopefully you received the utmost entertainment from chapter 14.